Hello students, in the previous session we studied about enthalpy of combustion, standard enthalpy of combustion and the problems related to enthalpy of combustion, Hess's law and formation enthalpies. Now let us see about the enthalpies of various types of reactions. The first one is enthalpy of atomization. What do you mean by atomization? Atomization means the formation of atoms from the molecules. So atoms form ಆಗುವಾಗ ಮಾಲಿಕ್ಯೂಲ್ಸಿನಲ್ಲಿರುವಂತಹ ಬಾಂಡ್ಗಳನ್ನು ಬ್ರೇಕ್ ಮಾಡುವ ಮೂಲಕ ನಾವು ಆಟಮ್ಸ್ಗಳನ್ನು ಫಾರ್ಮ್ ಮಾಡ್ತೇವೆ. ಸೊ ಆಟಮ್ ಫಾರ್ಮ್ ಆಗುವಾಗ ಯುಟಿಲೈಸ್ ಮಾಡುವಂತಹ ಎನರ್ಜಿ ಏನಿದೆಯೋ ಅಲ್ಲಿ ಆಗುವಂತಹ ಎಂಥಾಲ್ಪಿ ಬದಲಾವಣೆ ಏನಿದೆಯೋ ಅದನ್ನು ನಾವು enthalpy of atomization ಅಂತ ಕರಿತೇವೆ. So enthalpy of atomization is the enthalpy change on breaking one mole of bonds completely to obtain the atoms in the gaseous phase. So when we break the bonds, we have to break the bonds in the molecules to form the atoms, the corresponding atoms. So the energy change or the enthalpy change on breaking one mole of bonds completely to obtain the atoms in the gaseous phase, that enthalpy change is known as enthalpy of atomization or standard enthalpy of atomization. Here the subscript A indicates the enthalpy of atomization, delta A H naught, delta A H naught, which indicates the enthalpy of atomization. So enthalpy change on breaking one mole of bonds completely to obtain the atoms in the gaseous phase. Andre one mole of bonds anna ಬ್ರೇಕ್ ಮಾಡಿ ಅದು ಆಟಮ್ಸನ್ನು ಪ್ರೊಡ್ಯೂಸ್ ಮಾಡಲಿಕ್ಕೆ ಅದು ಯಾವ ಸ್ಟೇಟಲ್ಲಿ ಇರಬೇಕು, ಆಟಮ್ಸು ಗೇಷಿಯಸ್ ಫೇಸಲ್ಲಿ ಇರಬೇಕು. ಸೊ ಅಲ್ಲಿ ಆಗುವಂತಹ ಎಂಥಾಲ್ಪಿ ಬದಲಾವಣೆಯನ್ನು ನಾವು ಎಂಥಾಲ್ಪಿ ಆಫ್ ಅಟಮೈಸೇಷನ್ ಅಂತ ಕರಿತೀವಿ. ಫಾರ್ ಎಕ್ಸಾಂಪಲ್, ಹಿಯರ್ ವಾಟ್ ಹ್ಯಾಪನ್ಸ್, ದ ಬಾಂಡ್ಸ್ ಇನ್ ದ ಮಾಲಿಕ್ಯೂಲ್ಸ್ ವಿಲ್ ಬಿ ಬ್ರೋಕನ್ ಬೈ ಸಪ್ಲೈಯಿಂಗ್ ಎನರ್ಜಿ. ಸೊ ಬಾಂಡ್ ಬ್ರೇಕ್ ಆಗಲಿಕ್ಕೆ ಏನು ಮಾಡಬೇಕು? ವಿ ಹ್ಯಾವ್ ಟು ಸಪ್ಲೈ ಎನರ್ಜಿ, ದಟ್ ಈಸ್ ಇಟ್ ಈಸ್ ಎಂಡೋಥರ್ಮಿಕ್ ರಿಯಾಕ್ಷನ್. So we have to supply energy for the bonds in the molecule so that atoms will be formed. So the energy change during this process is enthalpy of atomization. For example, hydrogen molecule in the gaseous phase, it can convert into hydrogen atoms, two hydrogen atoms, that is by supplying energy by breaking the bonds between the hydrogen atoms in hydrogen molecule so that it will form gaseous form, that is hydrogen atoms in gaseous form. The enthalpy change during this process is 435 kilojoule per mole, that is one mole of bonds require 435 kilojoules of energy for breaking of the bonds to form the atoms. So this is enthalpy of atomization of hydrogen. Similarly, if you consider methane, in methane there are 4 CH bonds. So the enthalpy or the energy required to break these 4 bonds, that is 1 mole of bonds, is 1665 kilojoules per mole. This is nothing but enthalpy of atomization of methane. So enthalpy of atomization is nothing but the enthalpy change accompanies the breaking of 1 mole of bonds to give the atoms in the gaseous phase. That is known as enthalpy of atomization. Here enthalpy of atomization in case of diatomic molecules, it is nothing but the bond enthalpy, that is the energy required to break the bond. Next enthalpy is bond enthalpy. We know that while breaking the bonds we have to supply energy. So the energy required to break, the amount of energy required to break 1 mole of bonds of a particular type between the two atoms in the gaseous state of the substance. That is known as bond enthalpy or standard bond enthalpy. So here the subscript bond indicates delta bond H naught, means it is the standard bond enthalpy. So the amount of energy required to break the 1 mole of bond, to break 1 mole of bonds of particular type between the two atoms in the gaseous state of a substance. That is known as bond enthalpy. This bond enthalpy can be of two types. It may be bond dissociation enthalpy, that is the energy required to break the bonds, or sometimes in the substances involving more than one type of bonds, then or in the polyatomic substances we come across this mean bond enthalpy. In case of diatomic molecules, we can see bond dissociation enthalpy, the energy, the amount of energy required to break the bond. But in case of polyatomic molecules, the case is different. So let us see the example. Diatomic molecules. In breaking of the bonds, there is energy is absorbed, that is energy is required to break the bond. But for making of the bond, while making, the energy is released. This is known as bond enthalpy. So the energy required to break 1 mole of bonds of a particular type between the two atoms in the gaseous state of the substance is called bond enthalpy, or the energy released when bond is formed, that is also known as bond enthalpy. Let us see the case of hydrogen. So hydrogen molecule in the gaseous phase can break the bond, we can break this bond to form hydrogen in the atomic form, hydrogen atoms. The energy required to break this bond is known as energy required to break this bond is known as bond enthalpy here, that is known as the bond enthalpy. So here the bond enthalpy of hydrogen, that is it is a diatomic molecule, it is 435 kilojoule per mole. It is the bond enthalpy of hydrogen. Okay? So this bond enthalpy is nothing but atomization, energy of atomization, that is enthalpy of atomization in case of diatomic molecules. Let us consider a polyatomic molecule like methane. Here in methane there are 4 bonds between carbon and hydrogen, that is carbon is joined to 4 hydrogen atoms in methane molecule. So here the energies required to break all these 4 CH bonds are not same. In such a case, we express in terms of mean bond enthalpy, that is mean bond enthalpy. So in case of diatomic molecules, you usually call it as bond dissociation enthalpy in all the diatomic molecules. But in polyatomic molecules, in case of polyatomic molecules, we calculate the bond energy in terms of mean bond enthalpy. Because here in case of methane, if you consider in methane, first step, that is carbon bonded to 4 hydrogen atoms in methane. So while breaking one bond, first bond, it requires the energy, that is 427 kilojoule per mole. For breaking the second bond, the energy required is different. It is 439 kilojoule per mole, that is from CH3 to get CH2 gas and H2. So here the bond dissociation energy is 439 kilojoule per mole. Similarly, next one, if you break the bond from CH2 to get hydrogen and CH, here the bond dissociation energy is still different, it is still higher, that is 452 kilojoule per mole. In last one, that is the bond dissociation, the energy required to break the bond between carbon and hydrogen to get carbon and hydrogen in the gaseous phase of atoms is 347 kilojoule per mole. So if you sum up this, if you add all these 4 bond dissociation enthalpies, the energy required to break all the 4 bonds, it will be the bond dissociation enthalpy of methanol is 1665 kilojoule per mole, 1665 kilojoule per mole. Here, this energy is the energy required to break 4 bonds, energy required to break 4 carbon-hydrogen bonds. So, the mean energy or mean bond enthalpy or mean bond energy is, that is calculated 1 by 4 of this value, that is 1 by 4 of 1665. So, 416 kilojoule per mole is the mean bond enthalpy or mean bond energy of carbon-hydrogen bonds in methane. So, in case of polyatomic molecules, we calculate the mean bond enthalpy. That is the, here the energy required to break the each individual bond is different. It is not same in all the cases, even though similar types of bonds, but the energy required to break the bonds, different bonds, will be not same. That is why we use, even though they are of same types, the energy required is not same. So, we calculate the bond energy in terms of mean bond energy here. So, mean bond energy in case of that is in case of methane is, that is carbon hydrogen bond enthalpy, mean bond enthalpy in methane is 416 kilojoule per mole. So, this is how we can calculate bond enthalpy either in case in terms of bond dissociation enthalpy or mean bond enthalpy. So, in case of diatomic molecules, this bond enthalpy is nothing but bond dissociation enthalpy, but in case of polyatomic molecules, we calculate mean bond enthalpy. So, let us have some values here, some mean bond enthalpies of some of the atoms or some of the bonds is given here. So, carbon, hydrogen, the mean bond enthalpies, carbon, hydrogen bond, nitrogen, oxygen, phosphorus, silicon, single, these are the single bond enthalpies for these atoms. Similarly, some mean multiple bond enthalpies, nitrogen bond enthalpy is 418, nitrogen triple bond enthalpy is 946, carbon nitrogen bond enthalpy is 615, carbon nitrogen triple bond enthalpy is 891, carbon double bond enthalpy is 611 kilojoules, carbon triple bond enthalpy is 837, carbon oxygen bond enthalpy is 741, carbon oxygen triple bond enthalpy is 1017, carbon oxygen double bond enthalpy is 498. So, we can see here the single bond enthalpy is lesser because the bond strength is less than double bond or triple bond. So, if there is double bond or triple bond between the two atoms in a molecule, then the energy required to break the bond is higher. So, this is about the bond enthalpy. So, bond enthalpy is nothing but the energy required to break 1 mole of bonds of particular type between the atoms in the gaseous state of the substance. ಅಂದರೆ ಯಾವುದೋ ಒಂದು ಸಬ್ಸ್ಟೆನ್ಸ್ ಅಲ್ಲಿ ಇರುವಂತಹ ಬಾಂಡ್ 1 ಮೋಲ್ ಆಫ್ ಬಾಂಡ್ಸ್ ಅನ್ನು ಬ್ರೇಕ್ ಮಾಡಲಿಕ್ಕೆ ಆ ಸಬ್ಸ್ಟೆನ್ಸ್ ಯಾವ ಸ್ಟೇಟಲ್ಲಿ ಇರಬೇಕು, ಗೇಷಿಯಸ್ ಸ್ಟೇಟಲ್ಲಿ ಇರಬೇಕು. ಸೊ ಆ ಕೇಸಲ್ಲಿ ಆ ಬಾಂಡನ್ನು 1 ಮೋಲ್ ಆಫ್ ಬಾಂಡನ್ನು ಬ್ರೇಕ್ ಮಾಡಲಿಕ್ಕೆ ಬೇಕಾಗುವಂತಹ ಅಮೌಂಟ್ ಆಫ್ ಎನರ್ಜಿಯನ್ನು ನಾವು ಏನಂತ ಕರಿತೇವೆ, ಬಾಂಡ್ ಎಂಥಾಲ್ಪಿ ಅಂತ ಕರಿತೇವೆ. ಸೊ ಇಲ್ಲಿ ಬಾಂಡ್ ಎಂಥಾಲ್ಪಿಯನ್ನು ನಾವು 2 ಟೈಪಲ್ಲಿ ಎಕ್ಸ್ಪ್ರೆಸ್ ಮಾಡ್ಬೋದು, ಬಾಂಡ್ ಡಿಸೋಸಿಯೇಷನ್ ಎಂಥಾಲ್ಪಿ or mean bond enthalpy. Usually in case of polyatomic molecules we calculate the mean bond enthalpy. ಯಾಕಂದರೆ ಅಲ್ಲಿ ಈ ಒಂದು ಆ ಬಾಂಡು ಸೇಮ್ ಟೈಪ್ ಇದ್ದರೂ ಕೂಡ ಒಂದೊಂದು ಬಾಂಡಿಗೆ ಬೇಕಾಗುವಂತಹ ಎನರ್ಜಿ ಬೇರೆ ಆಗಿರ್ತದೆ, ಡಿಸೋಸಿಯೇಷನ್ ಮಾಡಲಿಕ್ಕೆ ಬೇಕಾಗುವಂಥ ಎನರ್ಜಿ ಬೇರೆ ಆಗಿರ್ತದೆ. ಅದನ್ನು ನಾವು ಈ ಮೀಥೇನ್ ಕೇಸಲ್ಲಿ ನೋಡಿದ್ದೀವಿ, ಬೇರೆ ಬೇರೆ ಎನರ್ಜಿ ಬೇಕು. ಇವೊಂದು ಇಟ್ ಇಸ್ ದ ಬಾಂಡ್ ಬಿಟ್ವೀನ್ ಕಾರ್ಬನ್ ಆ್ಯಂಡ್ ಹೈಡ್ರೋಜನ್, ಸೊ ಈಚ್ ಬಾಂಡಿಗೆ ಬಾಂಡ್ ಎಂಥಾಲ್ಪಿ ಸೇಮ್ ಇಲ್ಲ. So, in this case, in such type of case, that is in case of polyatomic molecules, we calculate mean bond enthalpy. So, this is about bond enthalpy and mean bond enthalpy. So, how we can calculate the enthalpy of reaction from bond enthalpies? Let us see. We already studied about this. So, the enthalpy of reaction is equal to bond enthalpies of the reactants minus bond enthalpies of the products. So enthalpy of a reaction, the enthalpy change of a reaction or standard enthalpy change of a reaction is equal to summation of bond enthalpies of the reactants and the minus the summation of bond enthalpies of the products. So let us see an example here. Calculate the enthalpy for the reaction H2 gas plus Cl2 gas gives 2HCl. So in this case, given that bond energies of hydrogen hydrogen, chlorine chlorine and hydrogen chlorine bonds are 433, 244 and 431 kilojoule per mole respectively. Kilojoule per mole respectively. So here we have to calculate the enthalpy of the reaction. How we can calculate the enthalpy of the reaction? So using the formula, here we have the formula, that is enthalpy of the reaction equal to bond enthalpies of the reactants minus bond enthalpies of the product. So what are the reactants here? Hydrogen and chlorine are the reactants. So bond enthalpies of hydrogen plus bond enthalpy of chlorine minus bond enthalpy of the product, that is bond enthalpy of hydrogen chloride. By using that formula, we can calculate the enthalpy of this particular reaction. So let us solve this. So enthalpy change for this reaction is equal to summation of bond enthalpy of reactants minus summation of bond enthalpy of products. So what are the reactants here? Hydrogen and chlorine. So bond enthalpy of hydrogen plus bond enthalpy of chlorine. So bond enthalpy of hydrogen is 433, bond enthalpy of chlorine is 244. So in the product side, 2 molecules of or 2 moles of HCl is formed. So minus 2 into bond enthalpy of HCl. So 2 into 431. So if you simplify this, we will get the enthalpy of reaction. The enthalpy of the reaction is, if you simplify this, 433 plus 244 minus 431 into 2, 862. So 433 plus 244 minus 862. So it comes out to be minus 185 kilojoule. Minus 185 kilojoule per mole is the enthalpy change during this reaction. So this is enthalpy change during the that is H2 plus Cl2 gives 2HCl. So minus 185 kilojoule means 185 kilojoules of energy is liberated. It is exothermic reaction. So this is how we can calculate the enthalpy of a reaction using bond enthalpies. This is an example. Okay, it's clear. Is it clear now? Next one is lattice enthalpy. We know ionic compounds usually they found in the crystalline form. They usually in the crystalline form. Lattice enthalpy of an ionic compound is the enthalpy change which occurs when 1 mole of an ionic compound dissociates into its constituent ions in the gaseous state. So the enthalpy change of an ionic compound is the enthalpy change which occurs when 1 mole of an ionic compound dissociates into its constituent ions in the gaseous phase. For example, sodium chloride, an ionic compound. Sodium chloride dissociates into its constituent ions, sodium and chloride. So if the ions formed in the gaseous phase, the energy required in this process, that is the enthalpy change when 1 mole of ionic compound dissociates into its constituent ions in the gaseous state. Here 1 mole of NaCl dissociates into its ions in the gaseous phase, sodium and chloride ions in the gaseous phase. The enthalpy change during this process is known as lattice enthalpy of that particular ionic compound. So it is in case of ionic compound, that is ionic compounds usually have crystal lattice, so crystal structure. So in such compounds, that is ionic compounds, this lattice enthalpy can be defined as the enthalpy change which occurs when 1 mole of an ionic compound dissociates into its constituent ions in the gaseous state. Or we can also define in other way. When ionic compound is formed, crystalline solid ionic compound is formed, energy will be released. So we can define lattice enthalpy in other way also, that is the energy released when 1 mole of a crystalline solid is formed by the combination of oppositely charged ions in the gaseous phase. It is also nothing but lattice energy or lattice enthalpy. So the energy released in the formation of 1 mole of a crystalline solid formed by the combination of oppositely charged ions in the gaseous phase, that is from the gaseous phase of the constituent ions we can get NaCl. So the energy released during the formation of 1 mole of such compound, such molecule, such crystalline solid is known as the lattice enthalpy of that compound. This lattice enthalpy cannot be determined directly. So we can determine the lattice enthalpy by indirect method. It is known as Born-Haber cycle. So here we utilize the Hess's law of constant heat summation for calculating lattice energy. So lattice energy is nothing but, or lattice enthalpy is nothing but enthalpy change which occurs when 1 mole of ionic compound dissociates into its constituent ions in the gaseous phase. So let us see how we can calculate lattice enthalpy by using Born-Haber cycle. In Born-Haber cycle, let us consider the NaCl only. So in this case, the energy change or enthalpy change which occurs in the dissociation, according to the definition, the enthalpy change which occurs when 1 mole of ionic compound dissociates into its constituent ions. So here this dissociates into sodium in the gaseous state and chloride in the gaseous state. So the energy change during this process is nothing but lattice enthalpy. Energy change during this process is nothing but lattice enthalpy. This value is 788 kilojoule. This value is 788 kilojoule plus 788 kilojoule per mole. That is, this much amount of energy is required to dissociate the sodium and chloride ions in the gaseous phase from sodium chloride crystal. So this is lattice energy of sodium chloride. This lattice energy cannot be determined directly, so we use the indirect method, that is Born-Haber cycle. So in this method we can calculate the lattice enthalpy using this cyclic process. So what happens? Initially sodium is in solid state. So sodium in solid state reacts with chlorine gas to give sodium chloride in solid state. The enthalpy of formation is given. So for this change to occur, this is the reaction. So this reaction can take place in number of steps. This reaction can take place in number of steps. That is, sodium in solid state can convert into sodium gas, then sodium gas converts into sodium ion in the gaseous phase, then chlorine molecule dissociates into chlorine atoms in the gaseous phase, then chlorine atoms gets converted into chloride ions, that is by the abstraction of electrons. So that is electron gain enthalpy. Then the sodium ion in the gaseous state and chloride ion in the gaseous state can combine to form NaCl. This is lattice enthalpy. The energy released here, the energy released when sodium ion and chloride ions get combined to form 1 mole of NaCl in the crystalline form. That is lattice enthalpy, energy released during this process. So this lattice enthalpy can be calculated using Born-Haber cycle in this case. So here, what is Born-Haber cycle here? First, sodium, we know the formation of sodium chloride, that is enthalpy change for the formation of sodium chloride from sodium in solid state, chlorine gas to give NaCl solid. So this, the enthalpy of formation of NaCl is minus 411.2 kilojoule is given. From this, we have to calculate the lattice enthalpy of this particular substance using Born-Haber cycle. Let us see how we can calculate that. First, in the first stage, sodium in the solid form, it gets converted into sodium in the gaseous form. So conversion of sodium solid into sodium gas. So it is known as sublimation process. The enthalpy change during this process is enthalpy of sublimation. This enthalpy of sublimation is 108.4 kilojoule per mole. Enthalpy of sublimation. Next, this sodium in the gaseous phase gets converted into sodium ion. Sodium atom gets converted into sodium ion in the gaseous phase. This is nothing but ionization reaction. Sodium atom gets ionized to sodium ion. The energy required for this process is nothing but ionization enthalpy or ionization energy. In third unit, you studied about that in periodic table, ionization enthalpy. So that is nothing but the energy required to ionize an atom. So here ionization enthalpy, that is delta HI, ionization enthalpy, it is plus 495.8 kilojoule per mole is the ionization enthalpy for sodium. Similarly, here chlorine molecule is there, so it dissociates into chlorine atoms. So chlorine molecule in the gaseous phase dissociates into chlorine atoms. So chlorine atoms can be obtained from chlorine molecule. Here the energy is the enthalpy of dissociation or bond enthalpy here. So it is the energy required to break this chlorine-chlorine bond. It is 121.0 kilojoule per mole. Then this chlorine atom gets converted into chlorine ion in the gaseous phase. That is, here electron is gained by the chlorine atom. Electron is gained by the chlorine atom. So it is, the energy is released, you know, that is electron gain enthalpy. You already studied about that, electron gain enthalpy. So energy, when an electron is added to a neutral atom, the energy is liberated. That liberated energy is known as electron gain enthalpy. So here the delta Eg, electron gain enthalpy, that is minus 348 kilojoule per mole. That is, here energy is released, 348 kilojoules of energy is released. So we have sodium ion in the gaseous phase and chloride ion in the gaseous phase. So these two get combined to form the sodium chloride solid. Here the energy liberated is nothing but it is lattice energy, that is minus U. This is nothing but the energy liberated during the formation of sodium chloride from its constituent ions in the gaseous phase. So this is lattice energy. So this lattice energy we have to find from this cyclic process by the method called Born-Haber cycle. So here we can use Hess's law of constant heat summation. So according to Hess's law of constant heat summation, the enthalpy of formation, it is a single step, though this reaction can take place in a number of steps. So the enthalpy of formation, that is delta H, that is enthalpy of formation of this reaction is equal to, we can apply Hess's law of constant heat summation, is equal to enthalpy of sublimation of sodium plus ionization enthalpy of sodium plus dissociation enthalpy plus or minus, it is electron gain enthalpy minus U. So this is a single step. So these are the different steps involved in the process. So we have the values of formation enthalpy of NaCl, sublimation enthalpy, enthalpy of sublimation, ionization enthalpy, dissociation enthalpy, electron gain enthalpy are the values already provided. These values are already provided. So if you substitute these values, we can get the lattice enthalpy. So if you substitute these values, so what are the values? Enthalpy of formation is minus 411.2, enthalpy of sublimation is 108.4, ionization enthalpy is 495.8 plus dissociation is 121.0 minus electron gain enthalpy is 348 minus U. So if you calculate this, if you simplify the values given here, we can get the value of U, that is ionization enthalpy. If you simplify this, we will get ionization enthalpy of sodium chloride 788.4 kilojoule per mole. So this is the lattice enthalpy of NaCl. So we calculate the lattice enthalpy using the Born-Haber cycle. It is an indirect method in which we can use Hess's law of constant heat summation for the intermediate steps, so that we can calculate the lattice enthalpy. Okay? So ಇಲ್ಲಿ ನಾವು ಲ್ಯಾಟಿಸ್ ಎಂಥಾಲ್ಪಿಯನ್ನು ಡೈರೆಕ್ಟಾಗಿ ನಾವು ಡಿಟರ್ಮೈನ್ ಮಾಡಲಿಕ್ಕೆ ಸಾಧ್ಯ ಇಲ್ಲದೆ ಇದ್ದಾಗ ನಾವು ಏನು ಮಾಡ್ತೇವೆ, ನಾವು ಹೆಸಸ್ ಲಾವನ್ನು ಯೂಸ್ ಮಾಡಿ ಇಂಡೈರೆಕ್ಟ್ ಮೆಥಡಲ್ಲಿ, ಅಂದರೆ ಬಾರ್ನ್-ಹೇಬರ್ ಸೈಕಲ್ ಮೂಲಕ ನಾವು ಲ್ಯಾಟಿಸ್ ಎಂಥಾಲ್ಪೀಸನ್ನು ಕ್ಯಾಲ್ಕುಲೇಟ್ ಮಾಡ್ತೇವೆ ಫಾರ್ ಅಯೋನಿಕ್ ಕಂಪೌಂಡ್ಸ್. ಸೊ ಇಲ್ಲಿ ಫಾರ್ ಎಕ್ಸಾಂಪಲ್ ಸೋಡಿಯಂ ಕ್ಲೋರೈಡ್, we want to calculate the lattice enthalpy of sodium chloride. ಇಲ್ಲಿ ಏನು ಮಾಡ್ತೇವೆ, ಸೋಡಿಯಂ ಸಾಲಿಡಿಂದ ಕ್ಲೋರಿನ್ ಮಾಲಿಕ್ಯೂಲ್ ಜೊತೆ ರಿಯಾಕ್ಟ್ ಆಗಿ ಸೋಡಿಯಂ ಕ್ಲೋರೈಡ್ ಸಾಲಿಡ್ ಆಗುವಾಗ ಆಗುವಂತಹ ಎನರ್ಜಿ ಬದಲಾವಣೆ, ಎಂಥಾಲ್ಪಿ ಬದಲಾವಣೆಯನ್ನು ಕೊಟ್ಟಿದ್ದಾರೆ. ಸೊ ಎಂಥಾಲ್ಪಿ ಚೇಂಜ್, ದಟ್ ಈಸ್ ಎಂಥಾಲ್ಪಿ ಆಫ್ ಫಾರ್ಮೇಷನ್ ಆಫ್ ಸೋಡಿಯಂ ಕ್ಲೋರೈಡ್. ಸೊ ಇದಿದ್ದಾಗ ನಾವು ಅಲ್ಲಿ ಲ್ಯಾಟಿಸ್ ಎಂಥಾಲ್ಪಿಯನ್ನು ಫೈಂಡ್ ಔಟ್ ಮಾಡಲಿಕ್ಕೆ ಈ ಎಲ್ಲ ಸ್ಟೆಪ್ಸನ್ನು ಫಾಲೋ ಮಾಡಬೇಕು. ಅಂದರೆ ಸೋಡಿಯಂ ಸಾಲಿಡ್ ಇರುವಂಥದ್ದು ಸೋಡಿಯಂ ಅಯಾನ್ ಆಗಿ, ಸೋಡಿಯಂ ಗ್ಯಾಸ್ ಆಗಿ ಕನ್ವರ್ಟ್ ಆಗ್ತದೆ. ಅಲ್ಲಿ ಆಗುವಂತಹ ಎನರ್ಜಿ ಬದಲಾವಣೆ, ಎಂಥಾಲ್ಪಿ ಬದಲಾವಣೆಯನ್ನು ನಾವು ಎಂಥಾಲ್ಪಿ ಆಫ್ ಸಬ್ಲಿಮೇಷನ್ ಅಂತ ಕರಿತೇವೆ. ಆಮೇಲೆ ಸೋಡಿಯಂ ಆಟಮ್ ಇದ್ದದ್ದು ಸೋಡಿಯಂ ಅಯಾನ್ ಆಗಿ ಕನ್ವರ್ಟ್ ಆಗ್ತದೆ. ಅಲ್ಲಿ ಆಗುವಂತಹ ಎನರ್ಜಿ ಚೇಂಜಸನ್ನು ನಾವು ಎಂಥಾಲ್ಪಿ ಆಫ್ ಅಯೋನೈಸೇಷನ್ ಅಂತ ಕರಿತೇವೆ. ಅದೇ ಥರ ಕ್ಲೋರಿನ್ ಮಾಲಿಕ್ಯೂಲ್ ಇದ್ದದ್ದು ಕ್ಲೋರಿನ್ ಆಟಮ್ ಆಗಿ ಕನ್ವರ್ಟ್ ಆಗುವಂತಹ ಎಂಥಾಲ್ಪಿ ಚೇಂಜಸನ್ನು ನಾವು ಎಂಥಾಲ್ಪಿ ಆಫ್ ಡಿಸೋಸಿಯೇಷನ್ ಅಂತ ಕರಿತೇವೆ. ಆಮೇಲೆ ಕ್ಲೋರಿನ್ ಆಟಮ್ ಇರುವಂಥದ್ದು ಕ್ಲೋರೈಡ್ ಅಯಾನ್ ಆಗಿ ಕನ್ವರ್ಟ್ ಆಗುವಂತಹ ದ ಎನರ್ಜಿ ಚೇಂಜಸ್, ದಟ್ ಈಸ್ ಎಲೆಕ್ಟ್ರಾನ್ ಗೇನ್ ಎಂಥಾಲ್ಪಿ. ದೆನ್ ಸೋಡಿಯಂ ion in gaseous state and chloride ion in gaseous state combine to form sodium chloride in solid state. The energy or the enthalpy change during this process is nothing but, that is energy released during this process is nothing but lattice enthalpy. We take it as minus U. because energy is released during this process. That is nothing but, according to definition, that is nothing but lattice enthalpy. So we can find out this lattice enthalpy by using Hess's law, by applying the principle of Hess's law of constant heat summation for the intermediate steps. So that by substituting the given values, we can calculate the lattice enthalpy of sodium chloride. So by using Born-Haber cycle. Okay, it's clear now. So this is about Born-Haber cycle and lattice enthalpy. Next is, if you put a solid ionic compound into a solvent. For example, if you put NaCl into a solvent, ಏನಾಗ್ತದೆ ಅಲ್ಲಿ? What will happen? ಈ ತರಹ ಪಾಸಿಟಿವ್ ಮತ್ತು ನೆಗೆಟಿವ್ ಅಯಾನ್ಸು ಏನಾಗಿರ್ತದೆ, ಒಂದು ಸಾಲಿಡಲ್ಲಿ ಈ ಥರ ಅರೇಂಜ್ಮೆಂಟಲ್ಲಿ ಇರ್ತದೆ. ವೆನ್ ಯು ಪುಟ್ ಇಟ್ ದಿಸ್ ಇಂಟು ಎ ಲಿಕ್ವಿಡ್ ಆರ್ ಸಾಲ್ವೆಂಟ್, the dissociation of the ions, constituent ions takes place. That is, the ions will be dissociated in the solvent. So this process is known as dissociation, solvation ಅಂತಲೂ ಕರಿತೇವೆ. ಈ ಪ್ರೋಸೆಸ್ ಆಗುವಾಗ ಅಲ್ಲಿ ಎಂಥಾಲ್ಪಿಯಲ್ಲಿ ಬದಲಾವಣೆ ಆಗ್ತದೆ. ಅಲ್ಲಿ ಎನರ್ಜಿ ರಿಲೀಸ್ ಆಗ್ಬೋದು ಅಥವಾ ಎನರ್ಜಿ ಅಬ್ಸಾರ್ಬ್ ಆಗ್ಬೋದು, ಎರಡೂ ತರಹ ಪ್ರೋಸೆಸ್ ಕೂಡ ಇರ್ಬೋದು. ಸೊ ಆ ಒಂದು ಎಂಥಾಲ್ಪಿ ಚೇಂಜಸ್ಸನ್ನು ನಾವು ಎಂಥಾಲ್ಪಿ ಆಫ್ ಸೊಲ್ಯೂಷನ್ ಅಂತ ಕರಿತೇವೆ. ದ ಎಂಥಾಲ್ಪಿ ಆಫ್ ಸೊಲ್ಯೂಷನ್ ಮೇ ಬಿ ಡಿಫೈನ್ಡ್ ಆಸ್ ದ ಚೇಂಜ್ ಇನ್ ಎಂಥಾಲ್ಪಿ ವೆನ್ 1 mole of substance is dissolved in a specified amount of solvent. ಅಂದರೆ 1 mole, ಯಾವುದೇ ಒಂದು ಸಬ್ಸ್ಟೆನ್ಸಿನ 1 ಮೋಲನ್ನು ಒಂದು ಸ್ಪೆಸಿಫೈಡ್ ಅಮೌಂಟ್ ಆಫ್ ಸಾಲ್ವೆಂಟಲ್ಲಿ ಅದು ಡಿಸಾಲ್ವ್ ಮಾಡಿದಾಗ ಅಲ್ಲಿ ಆಗುವಂತಹ ಎಂಥಾಲ್ಪಿ ಬದಲಾವಣೆಯನ್ನು ನಾವು ಎಂಥಾಲ್ಪಿ ಆಫ್ ಸೊಲ್ಯೂಷನ್, ಹಿಯರ್ ಡೆಲ್ಟಾ SOL, subscript SOL indicates enthalpy of solution, H0, standard enthalpy of solution. The enthalpy of solution is defined as the change in enthalpy when 1 mole of a substance dissolved in specified amount of solvent. Then it is called enthalpy of solution. If the solvent is water, if you use the solvent as water, if you use water as solvent, then the enthalpy change is known as enthalpy of hydration. ನಾವು ವಾಟರನ್ನು ಸಾಲ್ವೆಂಟ್ ಆಗಿ ಯೂಸ್ ಮಾಡೋದಾದರೆ ಅಲ್ಲಿ ನಾವು ಯಾವುದೇ ಒಂದು ಸಬ್ಸ್ಟೆನ್ಸನ್ನು 1 mole ಆಫ್ ಸಬ್ಸ್ಟೆನ್ಸನ್ನು ಡಿಸಾಲ್ವ್ ಮಾಡಿದಾಗ, ಕರಗಿಸಿದಾಗ ಅಲ್ಲಿ ಆಗುವಂತಹ ಎಂಥಾಲ್ಪಿ ಬದಲಾವಣೆಯನ್ನು ನಾವು ಏನಂತ ಕರಿತೇವೆ? ಎಂಥಾಲ್ಪಿ ಆಫ್ ಹೈಡ್ರೇಷನ್ ಆಫ್ ದಟ್ ಸಬ್ಸ್ಟೆನ್ಸ್. ಯಾಕೆಂದರೆ ಅಲ್ಲಿ ಸಾಲ್ವೆಂಟ್ ಯೂಸ್ ಮಾಡಿರುವಂಥದ್ದು ವಾಟರ್, ಅಥವಾ ಬೇರೆ ಯಾವುದೇ ಸಾಲ್ವೆಂಟನ್ನು ಯೂಸ್ ಮಾಡಿದರೆ ನಾವು ಇನ್ ಜನರಲ್ ವಿ ಕಾಲ್ ಇಟ್ ಆಸ್ ಎಂಥಾಲ್ಪಿ ಆಫ್ ಸೊಲ್ಯೂಷನ್. ಅಂದರೆ 1 mole, ಯಾವುದೇ ಒಂದು ಸಬ್ಸ್ಟೆನ್ಸ್ 1 mole ಡಿಸಾಲ್ವ್ ಮಾಡಿದಾಗ ಆಗುವಂತಹ ಎನರ್ಜಿ ಬದಲಾವಣೆ. ಫಾರ್ ಎಕ್ಸಾಂಪಲ್, ನಾವು ಶುಗರನ್ನು ವಾಟರಲ್ಲಿ ಡಿಸಾಲ್ವ್ ಮಾಡ್ತೇವೆ. ಅಲ್ಲಿ ಏನಾಗ್ತದೆ, ನೀವು ಮನೆಯಲ್ಲಿ ಅಬ್ಸರ್ವ್ ಮಾಡಿರ್ಬೋದು, ಜ್ಯೂಸ್ ಮಾಡುವಾಗ ವೆನ್ ಯು ಡಿಸಾಲ್ವ್ ಶುಗರ್ ಇನ್ ವಾಟರ್, ಯು ಕ್ಯಾನ್ ಅಬ್ಸರ್ವ್ ಇಫ್ ಯು ಟಚ್ ದ ಸರ್ಫೇಸ್ ಆಫ್ ದಟ್ ವೆಸಲ್ ಯು ಫೀಲ್ ಕೂಲ್. ಯಾಕೆ? ಇಟ್ ಈಸ್ ಎಂಡೋಥರ್ಮಿಕ್ ರಿಯಾಕ್ಷನ್. ಅದು ಏನು ಮಾಡ್ತದೆ, ಹೊರಗಡೆ ಅದರ ಸರ್ಫೇಸಲ್ಲಿ ಇರುವಂತಹ ಹೀಟನ್ನು ಹೀರಿಕೊಳ್ತದೆ. ಯಾಕೆಂದರೆ ಆ ಡಿಸೊಲ್ಯೂಷನ್ ಪ್ರೊಸೆಸ್ಸಲ್ಲಿ ಎಂಡೋಥರ್ಮಿಕ್ ಆಗಿರ್ತದೆ. ಸೊ ಇಟ್ ಅಬ್ಸಾರ್ಬ್ಸ್ ದ ಎನರ್ಜಿ ಫ್ರಮ್ ದ ಸರೌಂಡಿಂಗ್ಸ್. ಸೊ ಅದರ ಸರೌಂಡಿಂಗ್ಸ್ ಏನಾಗಬೇಕು, ಅಲ್ಲಿ ಹೀಟನ್ನು ಅದು ಒಳಗಡೆ ಅಬ್ಸಾರ್ಬ್ ಮಾಡಿದ್ರೆ ಸರೌಂಡಿಂಗ್ಸ್ ಕೂಲ್ ಆಗಬೇಕು. ಸೊ ವಿ ಫೀಲ್ ಕೂಲ್ ಎಫೆಕ್ಟ್. ಸೊ ಇಲ್ಲಿ 1 mole ನೀವು ಯಾವುದೋ ಎಷ್ಟೋ ಅಮೌಂಟ್ ಆಫ್ ವಾಟರ್ ತೊಗೊಂಡಿದ್ದೀರಿ, ಸ್ಪೆಸಿಫೈಡ್ ಅಮೌಂಟ್ ಆಫ್ ಸಾಲ್ವೆಂಟ್, ಅದಕ್ಕೆ 1 mole ಶುಗರನ್ನು ಹಾಕಿ ಡಿಸಾಲ್ವ್ ಮಾಡಿದಾಗ ಅಲ್ಲಿ ಏನು ಚೇಂಜಸ್ ಆಗಿದೆ, ಯಾವುದರಲ್ಲಿ? ಎಂಥಾಲ್ಪಿಯಲ್ಲಿ ಹೀಟ್ ಎನರ್ಜಿ ವ್ಯತ್ಯಾಸ ಏನಾಗಿದೆ, ಚೇಂಜಸ್ ಏನಾಗಿದೆ, ಅದನ್ನು ನಾವು ಏನಂತ ಕರಿತೇವೆ? ಎಂಥಾಲ್ಪಿ ಆಫ್ ಸೊಲ್ಯೂಷನ್ ಆಫ್ ಶುಗರ್. ನಾವು ಶುಗರನ್ನು ಡಿಸಾಲ್ವ್ ಮಾಡಿದಾಗ. ಅದೇ ಇನ್ನು ಶುಗರ್ ಡಿಸಾಲ್ಯೂಷನ್ನು ಎಂಡೋಥರ್ಮಿಕ್ ಪ್ರೊಸೆಸ್. ಕೆಲವು ಒಂದು ಸಬ್ಸ್ಟೆನ್ಸು ಡಿಸಾಲ್ವ್ ಆದಾಗ ಅಲ್ಲಿ ಎನರ್ಜಿ ಲಿಬರೇಟ್ ಆಗ್ಬೋದು, ಹೀಟ್ ಲಿಬರೇಟ್ ಆಗ್ಬೋದು. ಸೊ ಅಂಥ ಸಬ್ಸ್ಟೆನ್ಸಲ್ಲಿ ಎನರ್ಜಿ ಲಿಬರೇಟ್ ಆಗಿರ್ತದೆ. ಸೊ ಇನ್ ಜನರಲ್ ನಾವು ಎಂಥಾಲ್ಪಿ ಚೇಂಜ್ ಅಂತ ತಗೊಳ್ತೀವಿ. ಇಟ್ ಮೇ ಬಿ ಎನರ್ಜಿ ಅಬ್ಸಾರ್ಬ್ಡ್ ಆರ್ ಇಟ್ ಮೇ ಬಿ ಎನರ್ಜಿ ರಿಲೀಸ್ ಡ್ಯೂರಿಂಗ್ ದ ಪ್ರೊಸೆಸ್. So the enthalpy of solution may be defined as the change in enthalpy when 1 mole of a substance is dissolved in specified amount of solvent. ಇಲ್ಲಿ enthalpy of solution ಅನ್ನು ನಾವು ಇಂಡೈರೆಕ್ಟ್ ಆಗಿ ಮಾಡ್ಬೋದು. ಈಗ AB ಅನ್ನೋ ಒಂದು ಸಾಲಿಡ್, ಇಫ್ AB is a solid and its dissolved in a solvent, it dissociates into its ion. So this can be possible by calculating that is indirect method, that is lattice enthalpy. By knowing hydration enthalpy, we can calculate the enthalpy of solution of this substance. So it involves hydration enthalpy and lattice enthalpy. So the sum of hydration enthalpy and lattice enthalpy is nothing but enthalpy of solution. And sometimes we use the enthalpy of dilution. When we dilute a solution by adding specified amount of solvent, there may be some energy changes takes place. There may be some energy changes takes place. The change in enthalpy during the dilution process is known as enthalpy of dilution. ಸೊ ಡೈಲ್ಯೂಷನ್ ಮಾಡಿದಾಗ ಒಂದು ಸೊಲ್ಯೂಷನನ್ನು ನಾವು ಅದಕ್ಕೆ ಸ್ಪೆಸಿಫೈಡ್ ಅಮೌಂಟ್ ಆಫ್ ಸಾಲ್ವೆಂಟ್ ಹಾಕಿ ಅದನ್ನು ಡೈಲ್ಯೂಟ್ ಮಾಡಿದಾಗ ಅಲ್ಲಿ ಆಗುವಂತಹ ಎಂಥಾಲ್ಪಿ ಬದಲಾವಣೆಯನ್ನು ನಾವು ಏನಂತ ಕರಿತೇವೆ, ಎಂಥಾಲ್ಪಿ ಆಫ್ ಡೈಲ್ಯೂಷನ್ ಅಂತ ಕರಿತೇವೆ. ಸೊ ಇದೆಲ್ಲ ಎಂಥಾಲ್ಪಿ ಚೇಂಜಸ್, ಡಿಫ್ರೆಂಟ್ ಟೈಪ್ಸ್ ಆಫ್ ಎಂಥಾಲ್ಪಿ ಚೇಂಜಸ್. ಇನ್ ದಿಸ್ session we studied about the different types of enthalpies. That is, we studied about bond enthalpy, enthalpy of atomization, then we studied about that is bond dissociation enthalpy and the mean bond enthalpy, and also we studied about lattice enthalpy, calculation of lattice enthalpy using Born-Haber cycle. Then we studied about enthalpy of solution and enthalpy of dilution. So these are the enthalpies of different types of reactions. Okay? With this, let us end the session. Thank you.